Extinct animals represent the vanished architects of a biological world that thrived long before our species began to dream. Their silent histories are etched into the very crust of the planet. Scientists at the Smithsonian estimate that over 99% of all species to ever exist are now gone. If you find peace in uncovering these lost lineages, subscribing is a wonderful way to support our shared journey through deep time. Imagine the Earth as a massive, ancient library where most of the volumes have been lost to fire and flood. The fossil record serves as the surviving fragments of those books, offering us only a glimpse into the diverse lives that once claimed the soil and the seas. This vast expanse of time is often difficult for the human mind to grasp, as our entire recorded history occupies only a microscopic sliver of the planet's 4.5 billion-year existence. When we look back, we aren't just looking at a gallery of skeletons, but at a shifting, breathing tapestry of evolution. Extinction is frequently viewed through a lens of tragedy, yet in the context of geology, it functions as a necessary and creative engine. As older lineages fade away, they vacate ecological niches, allowing new and often more complex forms of life to emerge and flourish. This constant cycle of replacement has driven the biological innovation that eventually led to our own presence. These relaxing facts help us visualize an Earth that existed in a state of wild, untamed equilibrium for eons. Before the first human footfall, the world was already ancient, populated by creatures whose shapes might seem like something out of a fever dream or a myth. There were periods when the atmosphere was so rich with oxygen that insects grew to the size of birds, and eras where the oceans were ruled by predatory reptiles longer than city buses. Bedtime listening allows us the space to picture these landscapes without the noise of the modern world. We are traveling back through eras defined by the rise and fall of giants, where the only sound was the wind through prehistoric ferns or the heavy breath of a beast that no longer has a name. Science for Sleep reminds us that we are merely the latest inhabitants of a world that has been many different versions of itself. Looking into the deep past, we find that every creature, no matter how briefly it existed, played a role in the long, unbroken chain of life. Imagine a sea where the very concept of a skeleton had not yet been conceived. This was the Ediacaran period, a time stretching back over 500 million years, populated by organisms so strange they seemed to belong to a different planet. These creatures did not possess limbs, eyes, or complex digestive tracts as we understand them today. Instead, the ocean floor was draped in quilted, fractal patterns that resembled living carpets or delicate, air-filled mattresses. One of the most iconic figures from this era is Insomnia, a flat, rib-textured organism that could grow to over a meter in length. For decades, scientists puzzled over its true nature, debating whether it was a giant single-celled amoeba, a type of lichen, or a primitive fungus. However, a 2018 study published in the journal Science revealed the presence of fossilized cholesterol in these specimens, providing a chemical fingerprint that identifies them as some of the oldest known members of the animal kingdom. During this era, the oceans lacked the frantic violence that defines modern ecosystems. Paleontologists often refer to this time as the Garden of Ediacara because there is no evidence of predation. There were no mouths designed for crushing, no claws for grasping, and no defensive armor. Life existed in a sort of quiet stasis, absorbing nutrients directly through its skin or feeding on the thick microbial mats that coated the seabed like a velvet rug. Can you imagine the profound silence of an ocean where nothing had yet learned how to hunt? These soft-bodied pioneers occupied a world of gentle currents and chemical signals, existing for millions of years without the need for the calcium-rich protection of a shell. Because they lacked bones or teeth, these organisms were unlikely candidates for fossilization. Their bodies were composed of soft tissue that usually rots away completely, yet they were preserved through a rare geological fluke. Intense storms would occasionally dump fine silt or sand over the organisms, creating a death mask that hardened into sandstone. This process captured their impressions for eternity, leaving behind ghost-like imprints in the rock that look more like artwork than anatomy. As the Ediacaran period drew to a close, the rules of life changed forever. The sudden appearance of burrowing animals and the first true predators likely disrupted the peaceful microbial mats, leading to the rapid disappearance of these quilted wonders. While they left no direct descendants that we can easily recognize, their existence proves that evolution experimented with many radical forms before settling on the bilateral body plans we see today. They represent a lost branch of biology, a quiet, soft-bodied prelude to the explosion of diversity that followed in the Cambrian. Their story is told not through skeletons, but through the chemical traces and faint textures left behind in ancient clay. Following this era of peace, the world would soon discover the necessity of armor. The oceans transitioned from a garden of soft-bodied drifters into a theater of intense biological competition. This shift is defined by the sudden appearance of mineralized shells and skeletons within the fossil record. Creatures began extracting calcium carbonate and phosphate from the seawater to build defensive walls. Life was no longer content to simply absorb nutrients from the silt through thin membranes. Complex body plans emerged with specialized segments for swimming, crawling, and hunting. This era, known as the Cambrian explosion, saw the rise of the world's first true eyes. Vision changed the dynamics of the ocean forever by turning the environment into a transparent map of opportunity and danger. One of the most formidable hunters of this time was Anomalocris, a creature whose name translates to unusual shrimp. It possessed a pair of large, stalked compound eyes that granted it a panoramic view of the prehistoric seafloor. Research published in the journal Nature indicates these eyes contained up to 16,000 hexagonal lenses. This provided a level of visual acuity that likely surpassed almost every other organism in the sea. Imagine floating in a world of blurry shadows when suddenly a predator appears that can see you with crystal clarity. Do you find yourself imagining these ancient seas as vibrant, sunlit gardens or as dark, mysterious voids? Anomalocris used two serrated, curling appendages to pull prey into a circular, tooth-lined mouth. Its size reached nearly 3 feet in length, making it a terrifying behemoth compared to its tiny contemporaries. Nearby, the bizarre Opabinia drifted through the water column with an even more unconventional design. This animal featured 5 mushroom-shaped eyes arranged across the top of its head like a crown. These eyes likely allowed it to monitor for threats from every possible angle simultaneously. A long, flexible proboscis extended from its face, ending in a single grasping claw. This nozzle-like organ allowed it to vacuum up small organisms hidden deep within the soft sediment. It looked so strange that when the first reconstruction was presented at a scientific meeting, the audience reportedly laughed in disbelief. Such biological experimentation was common during this period of rapid diversification. Hallucigenia is perhaps the most famous example of the confusion these ancient forms caused for modern science. When paleontologist Simon Conway Morris first described it, he believed the creature walked on its rigid, stilt-like spikes. He theorized that the soft tentacles on its back were used to catch passing food from the current. Years later, better preserved fossils revealed that the creature had been studied upside down for decades. The spikes were actually defensive armor used to deter predators attacking from above. Its soft tentacles were its feet, equipped with tiny claws for navigating the uneven seafloor. This reversal serves as a poignant reminder of how difficult it is to interpret life from 500 million years ago. These developments sparked a relentless evolutionary arms race between species. As predators grew faster and more perceptive, prey species developed thicker carapaces and complex spines. Some animals even developed the ability to burrow deep into the mud to escape the gaze of the new hunters. This cycle of weaponry and protection drove the diversification of the entire animal kingdom. Every creature you see today carries the structural legacy of these early survival strategies. The peace of the Ediacaran had ended, replaced by a world defined by sight, speed, and armor. This was the moment life truly learned how to fight for its place in the sun. As the world moved into the Ordovician period, the oceans didn't just become more crowded, they grew significantly more complex through a phenomenon known as the Great Ordovician Biodiversification Event. This era saw a tripling of marine animal families, establishing a biological blueprint that would persist for hundreds of millions of years. Among the most formidable newcomers were the Eurypterids, creatures often referred to as sea scorpions. These weren't actually scorpions in the modern sense, though they shared a common lineage with today's arachnids and horseshoe crabs. Their segmented bodies were encased in heavy chitinous armor, allowing them to dominate the seafloor with a terrifying rhythmic grace. Imagine a predator the size of a modern saltwater crocodile, but possessing the anatomy of a nightmare-sized lobster. This was Gecalopterus, the largest arthropod ever known to have lived, reaching lengths of over 8 feet. It didn't just inhabit the deep ocean, it thrived in the murky, brackish waters of estuaries and river mouths, using massive, spiked pincers to snatch unsuspecting prey. Its compound eyes were sophisticated and large, providing the visual clarity needed to hunt in low-light environments where silt and shadow offered easy concealment for smaller organisms. While these giants ruled the water, their internal physiology kept them anchored to the aquatic realm for a very long time. Their heavy exoskeletons provided nearly impenetrable defense, but without the buoyancy of water to support their sheer mass, their legs would have buckled under the crushing weight of gravity on dry land. Their respiratory systems relied on book gills, which required a constant film of moisture to exchange oxygen, creating a biological ceiling that prevented a full transition to the shore. Have you ever found a fossil or a strange shell on a beach and wondered what kind of world it belonged to millions of years ago? At the same time these giants patrolled the shallows, a quiet revolution was occurring in the anatomy of early fish. The first jaws began to appear, evolving from the anterior gill arches that previously supported breathing. This structural shift transformed fish from simple filter feeders or bottom dwellers into active, biting predators. These primitive jawed fish, though small at first, represented a massive leap in evolutionary engineering. They could finally grip, tear, and manipulate their environment in ways their ancestors never could. This set the stage for a new hierarchy in the Silurian seas, where speed and biting force would soon challenge the dominance of the armored giants that had reigned for so long. Progress was slow, measured in the steady accumulation of bone and cartilage, but the path toward the modern vertebrate body plan was now firmly established. The transition into the Devonian period marked a turning point where the evolutionary experiments of the past consolidated into the specialized forms that define many modern lineages. While the Silurian established the foundations of the vertebrate body, the Devonian refined them through an era of intense biological competition often referred to as the Age of Fishes. At the height of this underwater hierarchy were the placoderms, a diverse group of armored fish that had no modern equivalents in terms of their physical construction. These creatures did not possess scales in the traditional sense. Instead, their bodies were encased in heavy, dermal bone plates that provided a nearly impenetrable defense against the primary predators of the era. The most formidable of these was Dunkleistus, a predator that reached lengths of nearly 10 meters and weighed several tons. Scientists studying the biomechanics of Dunkleistus have discovered that it lacked true teeth, instead utilizing sharpened bony plates that grew directly from its jaw. Do you remember the feeling of seeing a massive creature at an aquarium and wondering how it would look in the wild? These gnathal plates were self-sharpening, meaning that every time the fish closed its mouth, the upper and lower plates rubbed against each other to maintain a lethal, razor-like edge. This natural honing process ensured that the predator remained efficient throughout its entire lifespan without the need for tooth replacement. Research published by the Field Museum indicates that the bite force of Dunkleistus was approximately 6,000 to 7,400 newtons, making it one of the most powerful bites in the history of aquatic life. This force was concentrated at the tips of its shearing plates, allowing it to puncture the thick armor of other placoderms with ease. While these armored giants dominated the deep, a different kind of revolution was occurring along the shallow shorelines and the expanding terrestrial landscapes. The colonization of land by early plants had moved beyond simple mosses, leading to the development of the first true forests. Species like Archaeopteris, which possessed woods similar to modern conifers but reproduced via spores, began to carpet the continents. As these vast forests grew, they fundamentally altered the Earth's atmosphere through the process of photosynthesis, leading to a significant oxygen spike. This increase in oxygen levels is often cited by paleontologists as a catalyst for the increased body size seen in many Devonian organisms, as higher oxygen concentrations allow for more efficient metabolic function in larger bodies. Amidst this greening world, a transitional species named Tiktaalik rosei emerged as a bridge between the aquatic and terrestrial realms. Tiktaalik possessed a mixture of fish-like scales and gills alongside tetrapod-like features such as a functional neck and a sturdy ribcage. These relaxing facts about our planet's history offer a unique perspective for bedtime listening. Perhaps the most striking feature of Tiktaalik was the structure of its pectoral fins, which contained bones corresponding to a humerus, radius, and ulna. These primitive wrists allowed the creature to prop itself up in shallow water, a vital step toward the eventual colonization of land by vertebrates. This era of armored giants and pioneering explorers established the biological blueprints that would eventually lead to every land-dwelling animal alive today. This science for sleep exploration reminds us that the quiet rustle of modern leaves began with the heavy, oxygen-rich forests of the Devonian. As the Devonian gave way to the Carboniferous, the world transformed into a humid, emerald hothouse where the very air felt heavy with the pulse of life. Atmospheric oxygen levels climbed to an astonishing 35%, nearly double what we breathe today, fueling a biological explosion of scale. This hyperoxygenated environment bypassed the respiratory limitations of many creatures, allowing insects to grow to sizes that seem pulled from a fever dream. Imagine standing in a silent, misty grove of towering scale trees and seeing a flash of iridescent color against the green. That flash belonged to Meganeura, a predatory insect resembling a modern dragonfly but possessing the massive wingspan of a golden eagle. These aerial hunters navigated the thick atmosphere with ease, their oversized flight muscles powered by the sheer abundance of oxygen molecules. Have you ever wondered what the humming of wings that large would sound like in the stillness of a prehistoric afternoon? The density of the air made it more buoyant, acting almost like a thin liquid that supported the weight of these soaring giants. On the forest floor, the scale of life was equally humbling, dominated by the armored presence of Arthropleura. This was the largest land-dwelling invertebrate to ever exist, a relative of modern millipedes that stretched as long as a compact car. While its size might suggest a terrifying predator, chemical analysis of fossilized droppings, or coprolites, suggests Arthropleura was likely a gentle giant. It spent its days weaving through the rotting vegetation of the coal swamps, consuming massive quantities of decaying plant matter to sustain its enormous frame. These vast, waterlogged landscapes were dominated by lycopsids and giant horsetails that reached heights of over 100 feet. Because the fungi and bacteria capable of breaking down lignin had not yet fully evolved, dead trees did not rot. They simply piled up in thick, dark layers. Over millions of years, the weight of the earth compressed this organic matter into the deep coal seams that power much of our modern world. Navigating these dense, fog-heavy jungles required specialized senses beyond simple sight. Insects developed intricate antennae and sensory hairs to detect chemical signals and vibrations through the soup-like air, feeling the approach of a predator long before it emerged from the mist. The sheer pressure of the Carboniferous atmosphere allowed sound to travel differently, creating an acoustic world where every rustle of a fern was magnified. These ancient swamps were not just forests. They were biological machines, scrubbing carbon from the sky and burying it beneath the mud. This era of gigantism reminds us that the limits of life are often set by the chemistry of the air itself. Every piece of coal burned today is a compressed memory of that oxygen-rich empire, a sunless treasure formed from the fallen trunks of a world where giants were the masters of the earth. The transition from the lush, damp Carboniferous to the arid Permian set the stage for a new kind of master. You might picture a creature with a massive, skin-covered sail along its back, often sold in sets of plastic dinosaur toys, yet Dimetrodon was never a dinosaur. It belonged to the synapsid lineage, a group defined by a single opening behind each eye socket, a structural trait it shares with you and every other mammal on Earth today. While dinosaurs were still tens of millions of years away from their first appearance, these proto-mammals were already refining the blueprints of our own biology. The magnificent sail of Dimetrodon has long sparked debate among researchers, with many theorizing it functioned as a sophisticated thermoregulation device, allowing the animal to soak up the morning sun's warmth or radiate excess heat during the midday peak. Others suggest it served a more social purpose, acting as a vibrant billboard to attract mates or intimidate rivals across the dry Permian floodplains. As the climate of the supercontinent Pangaea grew increasingly harsh and dry, the sprawling forests retreated, leaving behind vast stretches of open, dusty terrain. This environment favored creatures that could travel longer distances and process tougher food. Enter the Gorgonopsids, the terrifying apex predators of their time. These were the world's first saber-toothed killers, possessing elongated canines designed to pierce the thick hides of their herbivorous cousins. They represented a significant leap in evolutionary engineering, developing a semi-erect gait that allowed for greater speed and agility than the purely sprawling posture of earlier tetrapods. It was during this period that the Great Divergence occurred, a quiet parting of ways between the lineage that would become the reptiles and the lineage that would eventually lead to us. While the ancestors of lizards and dinosaurs were perfecting the art of the egg and scaly skin, our synapsid ancestors were developing differentiated teeth, incisors for nipping, canines for tearing, and molars for grinding. This specialization of the jaw meant they could extract more energy from every bite, a necessary adaptation for surviving in a world where resources were becoming scarce. These early pioneers were also likely experimenting with higher metabolic rates, a precursor to the warm-bloodedness that defines modern mammals. To survive the interior of Pangaea, where seasonal temperature swings were brutal, synapsids began to evolve more efficient ways of breathing and conserving water. They were the architects of a new world order, one based on internal stability and metabolic endurance rather than just raw size. Looking back at these scaly, sailback giants, it is humbling to realize that the foundations of our own skeletons and the very shape of our skulls were being forged in the heat of a Permian desert. They were not a failed experiment of prehistory, but a vital link in the chain that allowed life to endure through one of the most volatile chapters in the history of our planet. The landscape of the late Permian did not end with a whimper, but with a series of geological convulsions that nearly extinguished the flame of life altogether. Imagine the ground in what we now call Siberia fracturing, not in a single explosion, but in a relentless, agonizing pulse of molten rock that persisted for hundreds of thousands of years. This was the birth of the Siberian Traps, a volcanic event of such staggering proportions that it flooded the surface with enough lava to bury the entire continental United States under nearly 1,000 feet of basalt. As the Earth tore itself open, it exhaled trillions of tons of greenhouse gases into the atmosphere, triggering a runaway global warming event that pushed the planet's thermostat to its absolute breaking point. The sky grew heavy with ash and toxic aerosols, but the primary engine of destruction was the invisible heat trapped by a thickening blanket of carbon dioxide and methane that sent global temperatures soaring. While the land scorched, the oceans began a slow, suffocating transformation that would eventually erase nearly every trace of life beneath the waves. Warm water holds less dissolved oxygen than cold water, and as the seas heated up, they stopped circulating, creating vast, stagnant dead zones known as anoxia. Compounding this disaster, the excess carbon dioxide reacted with the seawater to form carbonic acid, lowering the pH of the entire global ocean. This acidification was a death sentence for organisms with calcium carbonate shells, as the very water they lived in began to dissolve their protective armor. In the deep, dark layers of the stagnant sea, anaerobic bacteria flourished, belching toxic hydrogen sulfide gas into the water and eventually the air, poisoning the coastal shallows. Do you find yourself wondering how any creature could have navigated such a profound and multi-layered transformation of their environment? This era, famously known as the Great Dying, remains the most severe extinction event in the history of our planet. It is estimated by paleontologists that 96% of all marine species and 70% of terrestrial vertebrate species vanished, a biological erasure so complete it brought the Earth to the brink of returning to a world ruled exclusively by microbes. This was a bottleneck that squeezed the diversity of the entire planet into a tiny, fragile thread. Amidst the desolation of the early Triassic, one peculiar creature emerged as the unlikely heir to a broken world, the Lystrosaurus. About the size of a pig, with a pair of downward-pointing tusks and a sturdy, barrel-like body, this herbivorous dicynodont possessed a unique combination of respiratory efficiency and burrowing habits that likely allowed it to survive the thinning atmosphere and the intense heat. For a brief window of geological time, Lystrosaurus was so dominant that it accounted for 95% of all land-dwelling vertebrates, wandering across the vast, empty expanses of the supercontinent Pangaea as a solitary ghost of the Permian. The disappearance of the dominant Permian predators and the thinning of the mammal-like lineages cleared the ecological stage for a different group of reptiles to claim the throne. These were the archosaurs, the ruling lizards, whose efficient bird-like lungs and more upright posture provided a competitive edge in the oxygen-poor, hot environment of the post-extinction world. This massive vacuum acted as a total reset button for evolution, shifting the balance of power and setting the trajectory for the rise of the dinosaurs and the ancestors of modern crocodiles. Had the Siberian traps been slightly less intense, or had the ocean currents managed to maintain their flow, the history of life would have taken a fundamentally different path. If you find these stories of resilience and change fascinating, you might enjoy subscribing for more quiet explorations of our planet's deep past. The Great Dying was not just an end, but a brutal refinement, a trial by fire that determined which forms of life were hardy enough to inherit the coming Mesozoic era. The landscape of the Triassic was a testing ground where the ancestors of modern crocodiles and birds fought for dominance in a world still recovering from the Permian collapse. Among the most fearsome of these early rulers was Postosuchus, a massive Rauisuchian that prowled the floodplains of what we now call North America. Measuring up to 4 meters in length, this predator possessed a deep, narrow skull filled with serrated, dagger-like teeth and, remarkably, the ability to rise onto its hind legs to sprint. While it might look like a modern crocodile to our eyes, its limbs were tucked directly beneath its body rather than sprawling out to the sides, a hallmark of the Archosaur revolution. This upright posture was a monumental shift for terrestrial life, effectively solving a physiological hurdle known as carrier's constraint. By uncoupling the muscles used for locomotion from those used for breathing, these creatures could run and respire simultaneously, a feat their sprawling ancestors found physically impossible. During this same period, the very first dinosaurs were beginning to leave their marks in the fossil record, though they were far from the giants we often imagine. Creatures like Eoraptor and Herosaurus, discovered in the Esquigualasto Formation of Argentina, were agile, bipedal, and relatively small, often no larger than a medium-sized dog. They lived in the shadow of the more diverse and numerically dominant crocodile-line reptiles, which occupied almost every ecological niche from heavily armored herbivores to apex land predators. It is a common misconception that dinosaurs were immediately superior. For much of the Triassic, it was the crocodile-line archosaurs that appeared to be winning the evolutionary race. Do you find yourself wondering how such small, unassuming animals like Eoraptor eventually became the icons of the Mesozoic? The answer lies in a combination of metabolic efficiency and sheer environmental luck. The bird-line archosaurs, which include dinosaurs and pterosaurs, developed a sophisticated respiratory system involving air sacs, similar to those found in modern birds today. This allowed for a continuous flow of oxygen through the lungs, providing a massive advantage in the relatively oxygen-poor atmosphere of the Triassic period. As the era drew to a close, a series of massive volcanic eruptions known as the Central Atlantic Magmatic Province triggered another mass extinction event. This catastrophe devastated the crocodile-line archosaurs, wiping out the massive Rauisuchians and leaving only a few small lineages that would eventually evolve into modern crocodilians. With their primary competitors suddenly removed, the dinosaurs were poised to occupy the vacant niches. This transition from the Triassic to the Jurassic marked the true beginning of the Dinosaurian Golden Age, as they shifted from minor ecological players to the undisputed masters of the planet. While the land trembled under the weight of the first true dinosaurs, a separate lineage of reptiles returned to the ancient cradle of the sea to claim their own dominion. It is a common misconception to label these aquatic giants as dinosaurs, but they belong to entirely distinct branches of the reptile family tree. True dinosaurs are defined by their upright limb posture and specific hip sockets, features that do not apply to the flippered predators of the deep. These marine reptiles were contemporaries of the dinosaurs, occupying the vast interior seaways that covered much of the Earth during the Mesozoic era. Among the most specialized were the ichthyosaurs, creatures that provide one of the most striking examples of convergent evolution in natural history. Despite being air-breathing reptiles, they evolved a streamlined, fusiform body shape almost identical to modern dolphins and tuna. This similarity is not due to shared ancestry, but rather the unrelenting physics of moving efficiently through a dense liquid medium. Some specimens have been preserved so exquisitely in fine-grained shales that we can see the soft tissue outlines of their dorsal fins and tail flukes, structures that lack bone and would otherwise be lost to time. Perhaps most astonishing is the fossil evidence of ichthyosaurs giving birth to live young at sea. One famous specimen captures a mother in the very middle of the birthing process, proving these reptiles had fully bypassed the need to return to land to lay eggs. This was a necessary adaptation, as their rigid, fish-like bodies prevented them from crawling onto beaches without suffocating under their own weight. While ichthyosaurs mastered speed, the plesiosaurs and their short-necked relatives, the pliosaurs, developed a completely unique method of underwater locomotion. They utilized 4 large, wing-like flippers to effectively fly through the water, a biomechanical strategy that has no direct equivalent in any living vertebrate today. Most modern sea turtles rely primarily on their front flippers for propulsion, but plesiosaurs synchronized all 4 limbs to achieve incredible maneuverability and sudden bursts of acceleration. The long-necked plesiosaurs likely used their small heads to ambush schools of fish from below, their silhouettes blending into the murky depths. Conversely, the massive pliosaurs became the apex predators of the Jurassic seas, possessing skulls that could reach nearly 2 meters in length. You might remember the towering depictions of the pliosaur Liopleurodon in early nature documentaries, where it was portrayed as a 25-meter-long titan. More recent paleontological studies involving skull-to-body ratios suggest a much more grounded reality, with the largest specimens likely reaching about 6 or 7 meters in length. Even at this revised size, Liopleurodon was a formidable hunter with a bite force capable of crushing the shells of prehistoric cephalopods. The discovery of these marine giants was often fueled by the fierce rivalry of the 19th century bone wars. When Edward Drinker Cope first reconstructed the skeleton of the long-necked Elasmosaurus, he famously placed the skull on the tip of the short tail instead of the long neck. It was his rival, Othniel Charles Marsh, who pointed out the error, fueling a lifelong animosity that nonetheless propelled the field of paleontology forward. Do you find yourself more fascinated by the creatures of the deep or the giants that walked the earth? This era of discovery revealed that the Mesozoic oceans were just as diverse and dangerous as the continents they surrounded, filled with leviathans that redefined our understanding of reptilian biology. While the depths held their own terrors, the skies above the Mesozoic world were claimed by an entirely different lineage of giants that redefined the limits of vertebrate biology. Pterosaurs were the first vertebrates to achieve powered flight, evolving a method of aerial locomotion that differed significantly from the birds we see today. Among these masters of the air, Quetzalcoatlus stands as a marvel of natural engineering, reaching a height comparable to a modern giraffe when standing on the ground. It is difficult to picture a creature of such immense proportions folding its wings to walk among the ferns, yet its skeletal remains suggest it was remarkably capable on land. With a wingspan stretching nearly 36 feet, Quetzalcoatlus relied on a biological structure that maximized strength while minimizing mass to an extreme degree. The architecture of a pterosaur wing was not composed of feathers, but rather a sophisticated membrane of skin and muscle known as the patagium. This living tissue was stretched from the side of the body to an exceptionally elongated fourth finger, which acted as the primary structural spar for the entire wing. Have you ever wondered what it would feel like to glide on wings made of your own skin, sensitive to every change in air pressure and temperature? To prevent the membrane from fluttering or tearing during high-speed maneuvers, it was reinforced by internal structures called actinofibrils. These closely spaced, hair-like fibers provided the necessary tension and allowed the pterosaur to adjust the shape of its wing mid-flight, much like a modern pilot adjusts the flaps on a plane. Maintaining such a massive frame in the air required a skeletal system that was almost ethereal in its lightness. Pterosaur bones were pneumatic, meaning they were hollow and filled with air, supported by internal struts that provided structural integrity without adding significant weight. In some species, the bone walls were as thin as a millimeter, making them incredibly fragile but perfectly adapted for the physics of flight. This hollow bone structure was part of a larger, highly efficient respiratory system involving a complex network of air sacs. These sacs allowed for a unidirectional flow of air through the lungs, ensuring a constant supply of oxygen to the massive flight muscles, a trait they shared with both dinosaurs and modern birds. While many pterosaurs were built for soaring over oceans, Hatzegopteryx represents a more robust and grounded evolutionary path. Found in the late Cretaceous deposits of what is now Romania, this pterosaur possessed a much shorter, thicker neck and a wider skull than its relatives. Scientists believe Hatzegopteryx was the apex predator of its ecosystem, an island environment where large dinosaurs were notably absent. Instead of fishing from the waves, It likely stalked the terrestrial landscape, using its powerful beak to snatch up small dinosaurs and other prey. The mystery of how such heavy animals took off remained unsolved for decades until researchers identified the quadrupedal launch mechanism. Unlike birds, which use only their hind legs to jump into the air, pterosaurs used their powerful forelimbs to vault themselves upward. This pole vaulting motion allowed them to generate the massive amount of power needed to clear the ground, utilizing the same muscles for both launch and flight. By shifting the primary burden of takeoff to the wings themselves, pterosaurs could grow to sizes that would be physically impossible for any bird to achieve. This unique combination of hollow bones, high-efficiency breathing, and a four-legged spring made them the undisputed sovereigns of the ancient sky for over 150 million years. While the pterosaurs claimed the heights of the atmosphere, the ground beneath them trembled under the weight of the most massive biological machines to ever walk the earth. The sauropods represented the absolute limit of what vertebrate biology can achieve on land, pushing the boundaries of bone strength and circulatory efficiency. Species like Argentinosaurus and Patagodoton reached masses exceeding 70 tons, a weight comparable to a modern Boeing 737. Sustaining such a colossal frame required an architectural revolution in the skeleton. Instead of the solid, heavy bones we might expect, their vertebrae were complex masterpieces of weight reduction. These bones were riddled with deep cavities called pleurocoels, filled with air sacs that extended from the respiratory system. This essentially turned their massive spines into biological bridge girders, immensely strong yet remarkably light. This hollowed-out construction allowed a 30-ton animal to carry a neck long enough to reach the tops of trees without collapsing under its own gravity. The long neck of a sauropod served as a metabolic shortcut, allowing the animal to stand in one place and clear an entire swath of vegetation with minimal movement. However, this convenience created a profound cardiovascular challenge. To move blood from the chest up to a brain positioned 40 feet in the air, a sauropod's heart had to be exceptionally powerful. Estimates suggest their blood pressure must have been at least twice that of a human to overcome the relentless pull of gravity. Some paleontologists suggest that their necks were held more horizontally to mitigate this pressure, while others point to the possibility of sophisticated one-way valves in the neck veins to prevent blood from backflowing. It is a staggering thought to imagine a heart weighing over 400 pounds, beating with enough force to drive a column of fluid several stories high. Feeding these titans was a matter of pure volume, and the sauropod strategy was built for speed rather than refinement. Unlike modern mammals that spend hours grinding food with complex molars, sauropods did not chew. Their teeth were shaped like pegs or spoons, designed solely to rake leaves and branches into their mouths. Once swallowed, the vegetation entered a massive fermentation vat within the gut. Some species utilized gastroliths, smooth, swallowed stones, which tumbled around in a muscular gizzard to mechanically break down tough plant fibers. This lack of chewing was an evolutionary masterstroke. By skipping the time-consuming process of mastication, they could process hundreds of pounds of food every single day, fueling a growth rate that saw them increase from the size of a goose to the size of a house in just a few decades. Have you ever wondered what the world would sound like if animals of this scale still moved through our forests today? Despite their enormous size as adults, sauropods began their lives as surprisingly small, vulnerable creatures. They followed a reproductive strategy known as selection, which is more similar to modern sea turtles than to elephants. A single female would lay dozens of grapefruit-sized eggs in a shallow pit, covering them with soil and then walking away. There was no evidence of the prolonged parental care seen in many other dinosaur lineages. This meant the hatchlings emerged into a world of predators, relying on safety in numbers and incredibly rapid growth to survive. Thousands would perish, but the few that reached maturity would eventually become so large that they were effectively immune to any predator on the planet. This cycle of life ensured that the sauropods remained the dominant herbivores of the Mesozoic for over 100 million years, standing as a testament to the sheer endurance of high-performance biological engineering. Their existence proves that gravity is not an unbreakable ceiling, but a variable that life, given enough time, will always find a way to navigate. The transition from the slow-moving giants of the sauropod lineage leads us directly into the world of the apex predators, the theropods, who refined the art of the hunt over millions of years. While the popular image of Tyrannosaurus rex is often defined by a thunderous, earth-shaking roar, the biological reality was likely much more subtle and perhaps even more unsettling. Computed tomography scans of Tyrannosaurus skulls reveal massive olfactory bulbs, suggesting that their world was defined by a complex map of scents that we can barely imagine. This animal could likely track a carcass or a living herd from several miles away, moving with a level of sensory precision that rivals the most specialized modern scavengers. Their auditory systems were equally specialized, tuned specifically to pick up low-frequency sounds that would be nearly imperceptible to human ears. These infrasonic pulses could travel through dense forests and across open plains, allowing individuals to communicate across vast distances through deep, rumbling vibrations that might have been felt in the chest of any creature nearby. The mechanical engineering of the theropod skull provides a fascinating look into how different predators solved the problem of feeding. A Tyrannosaurus rex did not just bite, it crushed, with a bite force estimated at nearly 8,000 pounds per square inch, enough to pulverize solid bone and access the nutrient-rich marrow inside. This puncture-and-pull feeding strategy was supported by thick, banana-shaped teeth that were built to withstand lateral pressure without snapping. Contrast this with the earlier Allosaurus, which occupied a completely different ecological niche. The Allosaurus had a much weaker bite force, yet its skull was designed to withstand incredible vertical stress. This suggests it used its head like a biological hatchet, swinging its upper jaw down into prey to create deep, systemic wounds. Do you remember the first time you saw a dinosaur skeleton in a museum and felt that strange sense of scale? This diversity in hunting styles allowed different theropod lineages to thrive for tens of millions of years, adapting their physiology to the specific defenses of the herbivores they pursued. Perhaps no theropod has challenged our understanding of dinosaur biology more than Spinosaurus aegyptiacus. Long thought to be a land-dwelling predator that simply looked different, recent discoveries have painted a picture of a truly semi-aquatic lifestyle. The discovery of a broad, paddle-like tail fluke in 2020 confirmed that Spinosaurus was a capable swimmer, likely using lateral undulations to propel itself through the ancient river systems of North Africa. Its bones were unusually dense, a feature called pachyostosis which is commonly seen in modern aquatic mammals like manatees to help control buoyancy. With its long, crocodile-like snout and conical teeth designed for gripping slippery fish, Spinosaurus represents a radical departure from the typical theropod body plan, proving that this lineage was capable of reclaiming the water just as successfully as it dominated the land. In the shadows of these giants lived some of the most specialized and bizarre creatures to ever walk the earth, such as the enigmatic Deinocheirus. For nearly half a century, this dinosaur was known only from a pair of massive, 8-foot-long arms ending in formidable claws, leading many to imagine a predator of unimaginable proportions. When more complete skeletons were finally unearthed in the Gobi Desert, the reality was far more strange. A bulky, humpbacked animal with a toothless, duck-like beak and a sail along its spine. It was a giant ostrich mimic that had abandoned the pursuit of large prey to favor a diet of water plants and small fish, utilizing its massive claws to dig through river mud or gather vegetation. The story of the theropods is also a story of soft tissues and the evolution of feathers, which were once thought to be the sole province of birds. The discovery of Yutyrannus huali, a 9-meter-long relative of the T. rex covered in shaggy filaments, proved that even large predators utilized feathers for insulation and social display. These early feathers were likely more like hair or down, providing a vital layer of warmth that allowed theropods to remain active in cooler climates or during the night. From the crushing jaws of the tyrant kings to the delicate plumage of their smaller cousins, these animals were not mere monsters, but highly adapted organisms that responded to the pressures of their environment with remarkable evolutionary creativity. Nature took a turn toward the heavy-duty with the Ankylosaurus, a creature often described as a living tank. Its entire back was a mosaic of fused bony plates known as osteoderms, rooted directly into the skin to create a shield that even a Tyrannosaurus would find difficult to penetrate. The most famous feature of this herbivore was the heavy club at the end of its tail, formed by 2 oversized bony nodules. Paleontologists have used biomechanical modeling to determine that a swinging ankylosaur tail could generate enough force to shatter the ankles of an approaching predator. This defense wasn't just about weight. The vertebrae in the tail were stiffened by ossified tendons, turning the rear half of the animal into a rigid handle for its terminal weapon. While Ankylosaurus focused on blunt force, the Stegosaurus developed a more specialized deterrent known as the thagomizer. This cluster of 4 spikes at the end of the tail was capable of piercing bone, a fact supported by fossil evidence of Allosaurus vertebrae showing puncture wounds that matched the shape of these spikes. Along its back, the double row of kite-shaped plates has sparked intense debate for decades. While originally thought to be armor, their relatively thin structure and high concentration of blood vessels suggest they functioned as thermal radiators to regulate body temperature. They may have also served as a visual warning, perhaps even flushing with blood to change color and intimidate rivals. Communication took on a different form for the Parasaurolophus, which carried a long, hollow crest extending from the back of its skull. Computer modeling and 3D prints of these nasal passages have allowed scientists to recreate the sounds they might have made. These were likely deep, resonant bellows, vibrating at low frequencies that could travel for miles through dense prehistoric forests. This acoustic adaptation suggests a complex social structure where individuals could identify one another through sound alone. The Pachycephalosaurus solved its social challenges with a thick dome of solid bone atop its head, sometimes reaching 10 inches in thickness. Microscopic analysis reveals a unique internal structure of radiating fibers designed to distribute impact stress, protecting the brain during high-speed collisions. These animals likely engaged in flank butting or head-shoving matches to establish dominance within their herds. The evolution of the Triceratops reveals a similar focus on the head, though for different reasons. Its iconic frill was not just a shield. It grew and changed shape as the animal matured, indicating its primary role in species recognition and mating displays. This massive head was anchored by a powerful beak made of keratin, which worked like a pair of industrial shears to slice through the toughest fibrous plants of the Cretaceous. Behind this beak sat a battery of hundreds of teeth, constantly replaced as they wore down from the friction of grinding palm fronds and cycads. This constant replacement cycle ensured they could process the calories needed to sustain their multi-ton bodies. The peaceful rhythms of the Cretaceous were shattered in a single afternoon by a mountain of rock 10 kilometers wide. Moving at 20 kilometers per second, this celestial body struck the shallow waters of the Yucatan Peninsula with a force that defies easy calculation. Geologists have determined the asteroid arrived at a steep angle of roughly 60 degrees, a trajectory that maximized the amount of dust and sulfur ejected into the upper atmosphere. The kinetic energy released upon impact was equivalent to billions of atomic bombs, instantly vaporizing the seafloor and the asteroid itself. This was not merely a localized disaster. It was a total planetary reset. Within seconds, a plume of incandescent plasma and vaporized rock shot out toward the stars, transcending the atmosphere before gravity pulled the debris back down. Do you remember the first time you felt the radiating heat from a large bonfire on your face from across a yard? As this ejector re-entered the atmosphere, it functioned like trillions of tiny, glowing meteors, heating the air to temperatures comparable to an oven on broil. This thermal pulse ignited dry vegetation across entire continents, triggering a global firestorm that consumed forests where dinosaurs had thrived for millions of years. For the creatures on the surface, there was almost no refuge from the searing heat. The sky turned a bruised, hellish red as soot from the fires combined with the dust from the impact to veil the sun entirely. This period of intense, suffocating heat was followed by a chilling, prolonged darkness. Sulfur-rich rocks at the impact site had been pulverized, releasing massive quantities of sulfate aerosols that reflected the remaining sunlight back into space. A profound silence descended over the planet as the impact winter began, a period where global temperatures plummeted and the cycle of photosynthesis essentially stopped. Without sunlight, the delicate ferns and towering conifers that fed the massive herbivores perished first. This caused a domino effect that climbed the food chain, leaving the giant predators like Tyrannosaurus rex with nothing to sustain their immense metabolic needs. In the oceans, the collapse was equally devastating as microscopic phytoplankton, the foundation of the marine world, could no longer harvest energy from the sun. Researchers at the University of Texas have suggested that this darkness may have lasted for years, fundamentally altering the chemistry of the oceans and the atmosphere. Amidst this carnage, the ancestors of modern life found ways to endure through biological luck or specialized adaptation. Small mammals, often no larger than rodents, survived by retreating into deep burrows where the earth insulated them from the surface heat and the subsequent freezing temperatures. These creatures were often generalist feeders, capable of scavenging on roots, insects, or decaying matter that larger specialists simply could not utilize. Crocodilians and certain turtles survived because of their slow metabolisms and their association with freshwater environments, which proved more resilient than terrestrial or marine ecosystems during the collapse. The birds we see today are the literal descendants of the small, feathered theropods that managed to weather this storm. The physical proof of this specific day is etched into the very crust of the Earth in a thin, dark line of clay known as the KPG boundary. This layer contains a high concentration of iridium, an element that is extremely rare in Earth's crust but abundant in asteroids. Discovered by Luis and Walter Alvarez, this global chemical signature confirms that the extinction was not a slow decline but a sudden, violent interruption of life. Alongside the iridium, scientists find shocked quartz, grains of sand that have been physically deformed by the immense pressure of the impact, and tiny glass beads called tektites. These geological markers serve as a silent witness to the moment the age of reptiles ended and the slow, arduous rise of the mammals began. Looking back at the scale of this change, how do you think it feels to stand on the ground where such a massive history lies buried just a few meters beneath your feet? Over the millions of years that followed, life did more than just recover. It reinvented itself. While the forests of the world lay in ruin, a select group of survivors navigated the charred landscape on foot. The catastrophic collapse of global woodlands meant that for millions of years, there were no trees for birds to perch in, leading to the total extinction of every lineage that relied on arboreal habitats. Only a few lineages of small, ground-dwelling birds managed to endure, and as the planet slowly greened again, these survivors didn't just reclaim the sky, they reclaimed the role of the dominant hunter. In the absence of large mammalian predators, birds like Gastornis grew to massive proportions, standing nearly 7 feet tall with heavy, bone-crushing beaks. These creatures were a vivid reminder that the spirit of the theropod dinosaurs had not truly vanished. In South America, the forest racids, famously known as terror birds, evolved into even more specialized killers. These flightless giants possessed narrow, sharp beaks designed for a specific and lethal hunting technique. Rather than biting and holding their prey, biomechanical studies suggest they used a hatchet-like motion, striking downward with incredible speed and force to drive the tip of their beak into the skull or spine of their target. Imagine for a moment, if you were walking through a prehistoric grassland, would you prefer to face a silent mammalian cat or one of these towering, feathered sentinels? This resurgence of avian power was not limited to the continents. On isolated islands, a fascinating process called convergent evolution frequently stripped birds of their wings. Without ground predators, the high metabolic cost of flight became unnecessary, leading to famous flightless species like the dodo or the giant moa of New Zealand. This evolutionary path highlights the remarkable plasticity of the avian body. Modern birds still carry the skeletal blueprints of their raptor ancestors, from the wishbone that once braced the chests of hunters like Deinonychus to the hollow, air-filled bones that allowed for both lightness and strength. Even the way a bird breathes, using a system of air sacs to maintain a constant flow of oxygen, is a direct inheritance from the high-performance respiratory systems of extinct theropods. As the landscape shifted and mammals eventually grew to challenge them, these ancient avian titans slowly faded, leaving behind the diverse, feathered world we recognize today. In the sweltering, humid marshes of the Paleocene, a shadow moved beneath the water that redefined the limits of biology. This was the era of the snake king. Titanoboa ceruginoensis stretched 42 feet long and weighed more than a ton, a discovery made in the Sarajan coal mines of Colombia that you might want to subscribe for to see more prehistoric wonders. The sheer mass of this animal, equivalent to the weight of a modern rhinoceros, was only possible due to the unique climate of the era. Scientists used the physical dimensions of cold-blooded animals as a biological thermometer to calculate the ancient heat of our planet. Because reptiles rely on external heat to regulate their metabolism, a snake of this magnitude required a constant ambient temperature of roughly 91 degrees Fahrenheit to function. This metabolic requirement reveals that the Paleocene tropics were significantly warmer than the modern world, pushing the boundaries of what vertebrate life can endure. Imagine standing in a jungle where the air is so thick and warm that it fuels the growth of a creature the size of a school bus. Have you ever felt the heavy, humid air of a tropical conservatory and wondered how life might adapt to even higher temperatures? The Sarajan Formation where these fossils were found was once a vast, swampy river delta teeming with oversized prey and competitors. This environment hosted turtles with shells the size of a kitchen table and prehistoric crocodilians known as dinosaurids that reached lengths of 15 feet. Titanoboa occupied the absolute apex of this food chain, filling a niche similar to the modern green anaconda but on a vastly more terrifying scale. Its thickest point was wider than a human's waist, making it the heaviest snake to ever slide across the Earth's surface. Rather than using venom to hunt, this massive serpent relied on pure mechanical force to subdue its meals. It likely spent the majority of its life submerged in murky, slow-moving waters where its weight was supported by buoyancy. Using dark, mottled scales as camouflage against the muddy river bottom, it would wait for a giant lungfish or a young crocodile to venture within reach. The strike was near instantaneous, followed by the application of thousands of pounds of constrictive pressure. This force was sufficient to collapse the circulatory system of its prey almost immediately, ensuring a swift end in the shadows of the canopy. Do you find yourself imagining the silence of that ancient swamp, broken only by the ripple of water against a massive coil? The dominance of the Snake King was tied directly to the stability of the Earth's thermal profile. As the global climate began to shift and cool during the transition into later epochs, the energy required to maintain such a massive body became unsustainable. For an ectotherm, a decrease in ambient temperature directly impacts the ability to digest food and move efficiently. Eventually, the overheated world of the Paleocene faded, and the gargantuan serpents vanished, leaving their massive vertebrae to be compressed into the Columbian coal seams. This disappearance highlights how even the most formidable predators are ultimately at the mercy of the delicate balance of our planet's atmosphere. The Eocene dawned with a world transformed, a period of dramatic warming that invited life to test the boundaries of the shoreline. In the shallow estuaries of what we now call Pakistan, a creature no larger than a modern wolf began a journey that would eventually lead to the largest animals to ever grace our planet. This was Pakicetus, an animal that, to the untrained eye, would look like a slender, long-tailed dog, yet its bones tell a different story. Deep within its skull, a thickened bone known as the involucrum reveals its true identity as a cetacean, a specialized feature found today only in whales and dolphins. Do you find it strange to imagine a creature with fur and 4 legs stalking the water's edge as the direct ancestor of the blue whale? Pakicetus lived a life between two worlds, hunting for fish in the shallows but returning to the dry earth to rest and raise its young. As the millions of years rolled forward, the line between terrestrial and aquatic blurred further with the emergence of Ambulocetus. This animal, often called the walking whale that could swim, possessed short, powerful limbs and massive, webbed feet that functioned like oars. Its body was elongated and its snout grew longer, designed for a life of ambush. Scientists believe it moved much like a modern crocodile, lurking beneath the surface of brackish water and lunging at unsuspecting prey. Despite its heavy reliance on the water, Ambulocetus still retained the ability to walk on land, though its gait was likely clumsy and labor-intensive. This creature represents a beautiful, awkward middle ground in the history of life, proving that evolution often moves in increments rather than leaps. The environmental pressures of the Eocene favored those who ventured deeper into the abyss, leading to a migration of the senses. Over generations, the nostrils of these early whales began a slow, anatomical crawl from the tip of the snout toward the top of the head. This shift was a masterstroke of efficiency, allowing the animal to breathe while most of its body remained submerged, eventually forming the blowhole we recognize today. Simultaneously, the middle ear underwent a profound transformation to handle the density of water. While land mammals rely on the eardrum to vibrate in the air, these early whales developed fat pads in their lower jaws to funnel sound vibrations directly to the inner ear. This was the primitive foundation of the sophisticated echolocation and underwater hearing that defines the modern cetacean experience. By the late Eocene, the transition was nearly complete with the arrival of Basilosaurus. This massive predator stretched up to 60 feet in length, cutting a serpentine profile through the ancient Tethys Sea. Unlike its predecessors, Basilosaurus was fully aquatic, a master of the open ocean. Yet, tucked away near its tail were two tiny, vestigial hind legs, each only about a foot long. These miniature limbs were far too small to support its weight on land, serving as a biological memory of a terrestrial past that was rapidly fading. Its vertebrae were hollow and filled with fluid, providing buoyancy but limiting its ability to dive into the crushing depths of the deep sea. This transition marks one of the most complete and fascinating fossil records in evolutionary biology, showing how life can entirely reinvent itself when the tides of the world begin to change. While the whales claimed the seas, a different lineage of giants asserted dominance across the vast stretches of prehistoric Eurasia. This was the era of Paraceratherium, a creature that redefined the physical boundaries of what it meant to be a terrestrial mammal. Though it was a hornless relative of the modern rhinoceros, its proportions would have seemed alien to us, standing nearly 5 meters tall at the shoulder. Imagine a beast so massive that a human would barely reach its knee, its long, muscular neck reaching upward to claim the lush greenery of the high canopy. During the Oligocene, the landscape of Central Asia was a mosaic of dense woodlands and open floodplains, providing the immense caloric intake such a titan required. These animals moved through the world with a slow, deliberate grace, their pillar-like limbs supporting a body weight that could reach up to 20 tons. Living at such a scale presents unique biological challenges that smaller creatures never encounter. Heat dissipation becomes a primary concern when your internal volume is so much greater than the surface area of your skin. It is likely that Paraceratherium possessed physiological adaptations similar to modern elephants, perhaps utilizing specialized blood vessels or sparse hair to shed the warmth generated by its massive metabolism. Have you ever wondered what the air might have felt like, vibrating with the low-frequency rumbles of a herd this size moving through the brush? their reproductive cycles would have been equally stretched by the demands of their size. Biologists suggest that a female Paraceratherium might have carried her young for over 2 years, a staggering investment of time and energy that ensured the survival of a single, well-developed calf. This slow rate of replacement became a liability when the world began to shift toward a cooler, drier state. As the tectonic collision of India and Asia pushed the Himalayas toward the sky, the weather patterns of the continent were fundamentally altered. The lush forests began to thin, replaced by expansive grasslands that offered far less nutrition to a specialized high-level browser. Paraceratherium was a specialist in a world that was suddenly demanding generalists. Its skull, which could be over 4 feet long, was equipped with downward-pointing upper incisors and forward-pointing lower ones, perfect for stripping bark and leaves but ill-suited for the abrasive grasses of the plains. Without the dense foliage it relied upon, the colossus found its range shrinking, its populations fragmenting into smaller, more vulnerable groups. The rise of new, smaller competitors and changing migratory paths put further pressure on this ancient lineage. Eventually, the very size that had made them masters of their environment became an impossible burden to maintain in a changing climate. Their disappearance marks the end of an era where mammals challenged the legacy of the dinosaurs in sheer physical scale, leaving behind only massive bones in the sun-bleached earth of the Mongolian steppe to tell the story of their reign. Every stride they took once shook the ground, a testament to the brief moment when the Earth's climate allowed for the maximum expression of mammalian life. This loss of the megaherbivores shifted the entire ecological balance of the continent, allowing for the rise of the diverse ungulates we recognize today. While the gentle grazers of the ancient plains moved in predictable rhythms, a far more imposing shadow cast itself across the North American Badlands. These were the entelodonts, often nicknamed hell pigs, though they bore little true resemblance to the swine we know today. Scientific analysis of their skeletal morphology suggests they are more closely related to hippos and the ancestors of modern whales than to any pig species. The most formidable of these was Diodon, a massive scavenger predator with a skull nearly a meter long, dominated by crushing jaws that could splinter bone with ease. Walking on slender, two-toed feet, they possessed a deceptive speed that allowed them to patrol vast territories in search of carrion or vulnerable prey. Their most striking features were the large, bony flanges protruding from their cheekbones and lower jaws. Paleontologists believe these were not just for muscle attachment, but likely served as protective armor during brutal face-biting matches. Imagine standing in a quiet field and hearing the sudden, bone-chilling snap of those jaws echoing through the brush. We find evidence of this aggression in the fossil record, where skulls bear deep scars and puncture wounds that match the dental patterns of their own kind. These animals were built for endurance and conflict, filling a niche as the apex scavengers of their time. Their presence meant that no carcass went to waste, as their teeth were specialized for extracting every ounce of marrow from the hardest remains. They were the cleanup crew of the Eocene and Oligocene, yet they were also opportunists that could take down live prey when the moment was right. In the harsh environment of the Badlands, the entelodont became a symbol of raw survival, a creature that thrived on the edge of high-energy predation and efficient scavenging. Their heavy necks supported a massive weight, allowing them to swing their heads with enough force to ward off smaller predators like hyenodonts. As the climate shifted and the open woodlands transformed into vast, arid grasslands, These specialized titans found it harder to sustain their massive caloric needs. Their eventual disappearance marked the end of an era where brute force and bone-crushing power were the primary tools of the terrestrial scavenger. This vacancy in the ecosystem eventually paved the way for more agile, social predators to claim the open plains. South America functioned as a biological laboratory for nearly 60 million years, drifting in complete separation from the rest of the world's landmasses. This era of splendid isolation allowed evolution to explore pathways that seem almost alien compared to the fauna of other continents. Without the pressure of northern predators or competitors, native lineages flourished into gargantuan, specialized forms found nowhere else on Earth. One of the most striking results of this isolation was the glyptodon, a relative of the modern armadillo that grew to the dimensions of a compact car. Its entire body was encased in a rigid dome of bony plates known as osteoderms, providing a fortress-like defense against the occasional terror bird or saber-toothed marsupial. These shells were so large and durable that early human inhabitants of the continent are thought to have occasionally used them as temporary shelters or tombs. Some species within this group possessed a formidable weapon at the end of their tails, a heavy, spiked club made of bone that could shatter the limbs of an attacker with a single swing. Have you ever wondered what it would feel like to stand beside a creature that looks like a living, breathing tank? While the glyptodon focused on defense, other creatures like the macrochinia evolved into some of the most puzzling shapes in the fossil record. This long-necked herbivore resembled a humpless camel, yet it possessed three-toed feet similar to a rhinoceros and a skull with nasal openings positioned high on the forehead between the eyes. Biologists suggest this unique anatomy supported a short, muscular trunk, perhaps used for stripping leaves from branches or filtering dust while drinking from arid waterholes. DNA analysis and collagen sequencing have confirmed that these animals belonged to a group called Leptopterns, an entire order of mammals that has no living descendants today. Towering over these grazers was the Megatherium, the giant ground sloth, which stood as one of the largest land mammals to ever exist. Weighing as much as 6 tons, these behemoths were nearly as large as modern elephants, but their anatomy was designed for a different kind of life. Their massive, curved claws were used to pull down tree branches or dig for nutritious roots, and their skeletons reveal they walked on the outer edges of their feet to keep those claws from blunting. Despite their intimidating size, they possessed a surprising ability to balance on their hind legs and tail, forming a stable tripod that allowed them to browse on foliage far above the reach of any competitor. This unique ecosystem remained stable until the rising of the Isthmus of Panama created a land bridge, ending the continent's long seclusion. This geological event triggered the Great American Biotic Interchange, where northern species flooded southward and these specialized giants faced new, unprecedented pressures. The legacy of South America's isolation remains a profound example of how geography shapes the destiny of life, creating a world of wonders that thrived in a quiet, southern sanctuary for eons. The shifting of tectonic plates eventually brought an end to South America's long era of solitude as volcanic activity began to bridge the gap between continents. Roughly 3 million years ago, the Isthmus of Panama rose from the sea, creating a narrow strip of land that functioned as a biological highway. This event, known as the Great American Biotic Interchange, forever altered the tree of life by allowing two long-separated worlds to collide. Northern placental mammals, including early bears, camels, and large cats, began a slow but relentless trek into the southern sanctuary. Meanwhile, the specialized fauna of the south, many of whom had never seen a predator from the northern hemisphere, were suddenly forced into a struggle for survival. You might wonder if any of these ancient creatures would have recognized their modern descendants as they crossed those early land bridges. Among the most famous travelers to head south was Smilodon, the genus commonly referred to as the saber-toothed cat. Despite the popular name, Smilodon was not a tiger or even a close relative of any modern feline species. It belonged to an entirely separate subfamily called the Macarodontinae, characterized by a physique that was much more robust and heavy-set than a lion. Their massive forelimbs were built for wrestling, allowing them to pin down large herbivores like bison or ground sloths with sheer brute force. This physical power was necessary because their most famous feature, those long, curved canine teeth, was surprisingly delicate. If a Smilodon had tried to bite into a struggling animal's skull or spine, the teeth likely would have shattered against the bone. Instead, these predators utilized a highly specialized technique known as the canine shear bite. Once the prey was immobilized on the ground, the cat would use its immensely powerful neck muscles to drive the serrated teeth into the soft tissue of the throat. This would sever the carotid artery and windpipe almost instantly, resulting in a quick and efficient kill. Evidence of their life history is preserved within the fossil record, particularly in the density of remains found at the La Brea tar pits. Many Smilodon skeletons show signs of massive, debilitating injuries, such as crushed vertebrae or severe hip fractures, that had completely healed over years of life. This suggests a complex social structure where the pack cared for its wounded members, sharing food with those who could no longer hunt for themselves. While the northern predators were highly successful in the south, the migration was not entirely one-sided. Some southern species managed to move north and find lasting success in entirely new climates. The Virginia opossum is perhaps the most famous example, being a hardy marsupial that successfully colonized North America and persists to this day. Other migrants, like the giant ground sloths and glyptodonts, also made the journey northward, though they eventually succumbed to the pressures of the late Pleistocene. The fate of the southern terror birds, however, was far more tragic. These flightless, carnivorous giants had been the apex predators of South America for nearly 60 million years, using their massive, hooked beaks to strike down prey. As placental predators like wolves and cats moved into their territory, the terror birds found themselves outcompete for resources. The combination of environmental changes and the arrival of more efficient, pack-hunting mammals eventually drove these magnificent birds into extinction. This monumental exchange highlights how the physical joining of continents can spark a biological revolution, where some lineages find new horizons and others vanish into the silence of history. While the land bridges of the Americas were shifting the fates of entire lineages, the isolated continent of Australia was cultivating a cast of shadows that felt like something out of a fever dream. Imagine walking through an open eucalyptus woodland and encountering Megalania, a monitor lizard so immense it would have dwarfed its modern cousin, the Komodo dragon. These titans reached lengths of nearly 7 meters, making them the largest terrestrial lizards to ever roam the earth. They were ambush predators, relying on a combination of serrated teeth and a venomous bite to bring down prey many times their own size. Evolution in isolation often produces such exaggerated forms, where a lack of placental competition allows reptiles to reclaim the role of apex predator. Heavy footsteps would have also heralded the arrival of Diprotodon, the largest marsupial to ever live. This creature was roughly the size of a modern white rhinoceros, though its closest living relatives are the diminutive wombat and the koala. Unlike the sleek grazers of the northern hemisphere, Diprotodon was a lumbering giant that likely lived in small herds, moving through the scrubland in search of salt bushes and shrubs. Their massive skeletons have been found in the dry beds of Lake Calabana, suggesting that during periods of intense drought, these giants would congregate around receding water sources, often becoming trapped in the mud. Can you picture a landscape where a 3-ton wombat-like giant was a common sight during a morning stroll? In the canopy and the tall grass, a different kind of terror lurked in the form of Thylacoleo, the marsupial lion. This predator was not a feline at all, but a highly specialized descendant of herbivorous ancestors, essentially a predatory possum. It possessed a bite force more powerful than any known mammalian carnivore of its size, aided by unique, bolt-cutter teeth that could shear through bone and muscle with terrifying efficiency. Its retractable claws and powerful forelimbs suggest it was an expert climber, dropping from branches to secure a kill. These animals represent a masterclass in convergent evolution, where nature arrives at the same predatory solution through an entirely different genetic path. The disappearance of these giants remains one of the most fiercely debated chapters in paleontology, centering on a complex tug-of-war between human arrival and climate change. Around 50,000 years ago, the Australian continent began to experience a significant drying trend, which fragmented the lush habitats these specialists required to survive. However, the timing of their extinction closely aligns with the arrival of the first humans, leading many researchers to suggest that even low-intensity hunting or landscape fire management could have pushed a fragile system over the edge. It is likely that a synergy of both factors created a perfect storm that these giants simply could not weather. Giant marsupials faced a distinct disadvantage compared to placental mammals due to their unique reproductive constraints. Because marsupials give birth to highly underdeveloped young that must complete their growth in a pouch, their metabolic investment is front-loaded and slow. Larger bodies mean longer weaning periods and slower replacement rates for the population. This biological bottleneck meant that once the mortality rate of adults increased even slightly, the species could not reproduce fast enough to recover. This inherent vulnerability turned their greatest strength, their massive size, into a terminal liability as the world around them began to change. As we look back on these Dreamtime giants, we see a testament to the fragile balance between a species' specialized success and the unforgiving shifts of a changing planet. While the southern reaches of the globe saw the decline of these giants, the frozen northern frontier nurtured a different breed of survivor, beasts wrapped in thick wool and fat. The woolly rhinoceros, known to science as Coelodonta, was a tank of the steppe tundra, possessing a unique, flattened horn that it likely used as a snow shovel to reach the dormant grasses buried beneath the frost. Unlike the rhinoceros species we recognize in warmer climates today, this creature thrived in a specialized niche where temperatures frequently plummeted far below zero. It shared this landscape with the cave bear, a massive predator that, interestingly, relied almost entirely on a vegetarian diet. Stable isotope analysis of their bones suggests these bears were largely herbivorous, spending their winters in deep hibernation within limestone caverns where many of their remains are still found today. Have you ever wondered what it might feel like to stumble upon such a massive, silent skeletal guardian in the dark? These bears were not alone in the shadows, as the cave lion patrolled the fringes of the mammoth steppe, growing up to 10% larger than the modern African lions seen on the savanna. This environment was not a barren wasteland of ice but a highly productive, cold grassland system fueled by intense sunlight and nutrient-rich soil. The lack of heavy forest cover allowed the wind to sweep the ground clear, maintaining a biome that supported millions of large mammals simultaneously. Because the ground in these regions remained frozen for millennia, we have been gifted with extraordinary preservation that goes far beyond simple bone fragments. Permafrost acts as a natural biological vault, keeping soft tissue, muscle, and even stomach contents intact for tens of thousands of years. Scientists have successfully extracted high-quality DNA from these frozen specimens, allowing us to map the genomes of animals that haven't walked the Earth in 10 lifetimes. This level of detail reveals the thickness of their undercoat and the specific proteins in their blood that acted as a natural antifreeze. As the climate fluctuated, the boundaries of this steppe shifted, forcing these specialists to migrate across vast land bridges that connected continents now separated by deep seas. The sheer scale of this ecosystem reminds us that the Earth's history is a series of interconnected pulses, where life finds a way to flourish in the most extreme conditions. The resilience of these species, captured in the stillness of the ice, provides a window into a world where the cold was not an enemy to be feared, but a foundation for a complex and thriving biological empire. Standing as the undisputed sovereign of the Pleistocene tundra, the woolly mammoth serves as a profound testament to biological ingenuity. Their bodies were not merely large. They were meticulously engineered for a world where temperatures routinely plummeted far below what modern elephants could endure. Underneath a shaggy coat of coarse guard hairs and fine wool, these giants possessed specialized sebaceous glands that secreted a thick layer of oil to waterproof their fur. This natural rain slicker ensured that moisture never reached their skin, preventing the deadly chill of evaporation in sub-zero winds. Evolution even redesigned their very lifeblood to combat the frost. Scientists have discovered that mammoth hemoglobin underwent a specific genetic mutation, allowing it to release oxygen to tissues even at near-freezing temperatures, a feat that would cause the blood of a modern elephant to fail. Small, fur-lined ears and a remarkably short tail further reduced the surface area from which precious body heat could escape into the biting air. The social fabric of these creatures was woven with a complexity that rivals our own, a fact revealed by the silent testimony of fossilized trackways. These preserved footprints tell stories of matriarchal herds where experienced females led younger generations across the vast mammoth steppe. Mass death sites, occasionally found in the permafrost, suggest that these animals shared deep emotional bonds, often staying with injured or dying kin until the end. Have you ever wondered if these ancient giants felt the same sense of loss we do when a member of the family is gone? Such gatherings of remains often point to a collective struggle against sudden environmental shifts or the strategic prowess of early human hunters. Our ancestors did not merely witness these titans. They were inextricably linked to them through a relationship of necessity and reverence. Every part of the mammoth was a gift of survival in the harsh Paleolithic landscape. Beyond the calorie-dense meat, their massive tusks and sturdy bones provided the structural framework for dwellings in regions where timber was non-existent. Soft ivory was carved into the world's first masterpieces of art, while their thick hides were fashioned into heavy blankets and protective clothing. This profound connection is immortalized in the flickering torchlight of cave paintings, where early artists rendered the mammoth with a level of detail that suggests deep observation and perhaps a touch of spiritual awe. As the world warmed and the great grasslands retreated, the mammoths faced a fragmenting world, leading to one of the most haunting chapters in natural history. On the remote, windswept expanses of Wrangel Island in the Arctic Ocean, a small population of pygmy mammoths survived in isolation long after their mainland cousins had vanished. These resilient survivors continued to roam their island sanctuary while the Great Pyramids were being constructed in Egypt, unaware that they were the final echoes of a dying age. Their smaller stature was a classic evolutionary response to limited island resources, a process known as insular dwarfism. The preservation of these animals is so extraordinary that it often blurs the line between paleontology and biology. The discovery of Yucca, a young female mammoth found in the Siberian permafrost, changed everything we thought we knew about the quality of ancient remains. She was found with much of her ginger-colored fur intact, and even her brain tissue was remarkably well preserved after 39,000 years. In some specimens, scientists have even found liquid blood and undigested wildflowers still resting in their stomachs. This level of detail allows us to see the mammoth not as a dusty relic, but as a living, breathing creature of muscle and pulse. It is this incredible preservation that fuels ongoing discussions about the ethics and possibilities of de-extinction, a bridge between the distant past and a technologically advanced future. If you find these glimpses into the ancient world as captivating as I do, subscribing is a wonderful way to ensure we continue this exploration together. The woolly mammoth remains a silent guardian of the ice, a reminder of the delicate balance between a species and the climate that sustains it. The story of the Irish elk is one of the most striking examples of biological ambition meeting the cold reality of environmental change. Despite its common name, Megaloceros giganteus was not strictly Irish, nor was it an elk. It was a giant deer that roamed the vast expanses of Eurasia, from the plains of Ireland all the way to the mountains of Siberia. Its most defining characteristic was the sheer, breathtaking scale of its antlers, which could reach a span of 12 feet from tip to tip. To hold this image in your mind is to realize the incredible physical burden these animals carried, with the antlers alone weighing up to 90 pounds of solid bone. What makes this even more remarkable is that these massive structures were shed and regrown every single year. This annual cycle placed a metabolic demand on the stag that is almost unparalleled in the animal kingdom. To produce such a vast amount of bone in just a few months, the deer had to consume enormous quantities of mineral-rich plants. During the peak of the growth season, the stags likely experienced a form of temporary, physiological osteoporosis, pulling calcium and phosphate from their own skeletal reserves to fuel the development of their headgear. This process was driven by what biologists call runaway selection, a phenomenon where a specific trait becomes so heavily favored by mates that it reaches an evolutionary extreme. For a time, the open, mineral-heavy grasslands of the Pleistocene provided everything the giant deer needed to sustain this display. But as the planet moved away from the glacial maximum, the landscape underwent a fundamental transformation. The wide-open tundras began to close as rising temperatures encouraged the growth of dense, tangled forests. In these new, wooded environments, a 12-foot span of antlers was no longer a symbol of strength. It was a catastrophic liability. A stag with such a wide reach would find it nearly impossible to navigate a thicket of trees while fleeing a predator or searching for food. The transition from the nutrient-dense willow and shrubs of the tundra to the more acidic, nutrient-poor soil of the encroaching forests meant the deer were essentially starving for the building blocks of their own identity. They did not vanish overnight, surviving in pockets of habitat until roughly 8,000 years ago. Ultimately, the very tools that had ensured their reproductive success for millennia could not navigate the closing canopy of a changing world. Isolation acts as a potent catalyst for evolutionary divergence, particularly when land masses are separated by the sea. This biological phenomenon is famously summarized by Foster's rule, which suggests that once a species becomes stranded on an island, the constraints of its new environment dictate a drastic change in physical scale. Large mammals often find that their traditional size is a liability in a landscape with finite food supplies, leading over generations to the emergence of island dwarfs. Smaller creatures may expand to fill ecological niches left vacant by absent predators, resulting in the remarkable sight of island gigantism. This peculiar balancing act transformed the Mediterranean islands into a home for the dwarf elephants of Cyprus and Sicily. Standing barely 3 feet tall at the shoulder, these miniature proboscideans were descendants of much larger mainland ancestors. Their fossilized skulls, featuring a large central opening for the trunk, likely inspired ancient Greek legends of the one-eyed Cyclops when early civilizations stumbled upon their remains. It is fascinating to consider how early humans might have interpreted these strange, weathered bones without the context of modern paleontology. Madagascar once served as the stage for one of the most imposing birds to ever walk the earth. The Epiornis, or elephant bird, was a flightless giant that weighed nearly half a ton, standing as a testament to the power of isolated evolution. Though it lacked the ability to soar, its presence was undeniable, evidenced by the discovery of eggs that remain the largest ever produced by any vertebrate. These massive vessels could hold the volume of roughly 7 ostrich eggs or over 160 chicken eggs. In the absence of large mammalian hunters, the elephant bird thrived for millennia until human arrival and habitat shifts altered the delicate equilibrium of its forest home. New Zealand offers a different perspective on this isolated trajectory through the history of the moa and its primary predator. Without ground-dwelling mammals to compete for resources, the moa evolved into a variety of flightless forms, with the largest species reaching heights of 12 feet. To balance the scales of this unique ecosystem, the Haast's eagle emerged as the largest eagle known to science. This raptor possessed claws as large as tiger talons, specifically adapted to strike down prey much heavier than itself from the air. When the moa populations began to decline due to overhunting and habitat loss, the Haast's eagle followed them into extinction, proving that even the most formidable specialist is vulnerable when its primary food source vanishes. On many of these remote islands, the lack of terrestrial predators encouraged birds to abandon the energy-intensive demand of flight altogether. Ground nesting became a viable strategy, allowing species to redirect their metabolic resources toward body growth rather than maintaining heavy flight muscles. This vulnerability became a fatal flaw when seafaring humans introduced rats, pigs, and cats to these closed systems. Do you find yourself drawn more to the mystery of the deep past or the visible remnants of these creatures in modern museums? The transition from safety to total exposure happened with staggering speed, leaving these specialized giants and dwarfs unable to adapt to the sudden presence of clever, hungry newcomers. New Zealand was once an archipelago of birds, a place where evolution took a turn toward the strange and the magnificent. Before the arrival of humans, 9 distinct species of moa roamed these islands, ranging in size with a diversity that mirrored the mammals found on other continents. The smallest, the bush moa, stood about the height of a modern turkey, navigating the dense undergrowth with a quiet, low-slung efficiency. In contrast, the heavy-footed moa and the giant moa reached heights that seem almost mythical today. A female South Island giant moa could stretch her neck toward the canopy nearly 12 feet above the ground, weighing over 500 pounds. These giants were not just tall, they were robust, built with thick legs that supported their immense weight as they moved through the ancient beech forests. Perhaps the most striking anatomical feature of the moa is what they lacked entirely. While other flightless birds like the ostrich or the kiwi still possess vestigial wing bones tucked beneath their feathers, the moa lost theirs completely. They are the only birds known to science to have absolutely no trace of wing structures, a result of millions of years of evolution in an environment where flight was unnecessary and wings offered no survival advantage. This extreme specialization made their skeletons unique, with a smooth shoulder girdle that lacked even the socket for a humerus. Their entire physiology was dedicated to the ground, focusing all their energy into powerful legs and a long, flexible neck designed for reaching the diverse flora of the New Zealand landscape. In the absence of deer, goats, or cattle, these avian giants stepped into the role of primary browsers. They shaped the very architecture of the forest, grazing on everything from low-lying ferns to the high branches of the broadleaf trees. We know exactly what they ate because the dry conditions of certain caves have preserved their gizzard contents for centuries. Researchers have discovered masses of seeds, twigs, and leaves, often accompanied by smooth, polished gizzard stones known as gastroliths. These stones, some the size of a human fist, acted as a biological mill, grinding down the tough, fibrous vegetation that made up their diet. This relationship between the birds and the plants was so deep that many New Zealand trees evolved divarication, a growth pattern of tangled, zigzagging branches and small leaves, specifically to protect themselves from the moa's powerful, shearing beaks. The end for the moa came with a speed that is difficult to comprehend in geological terms. When the first Polynesian settlers arrived in the late 13th century, they found a population of birds that had never known a land-based predator. This lack of fear, combined with a slow reproductive rate, made the moa incredibly vulnerable. Archaeological sites across both islands reveal massive middens filled with the charred bones of thousands of birds. Estimates suggest that within less than 200 years, perhaps even as few as 100, every single species of moa was gone. It was one of the fastest megafaunal extinction events in history, a biological collapse that transformed the islands forever. Do you find it harder to process the loss of a giant species or the disappearance of the smaller, hidden ones that often go unmentioned? The silence they left behind in the forests still resonates, a reminder of how quickly a kingdom can vanish when the balance of an ecosystem is suddenly and irrevocably shifted. The most famous inhabitant of these lost worlds is undoubtedly the dodo, a bird whose very name has become a synonym for obsolescence and cognitive failure. This reputation is fundamentally misplaced, born from a deep misunderstanding of how evolution shapes the mind and body in isolation. In reality, the dodo was a highly specialized, giant member of the pigeon family, technically known as Rhaphis cucullatus. For millennia, it thrived on the volcanic island of Mauritius, occupying an ecological niche that required no flight and, perhaps more importantly, no fear. Because there were no large predatory mammals on the island before the arrival of humans, the dodo never developed a flight or fight response to terrestrial threats. When Portuguese and Dutch sailors arrived in the late 16th century, the birds approached them with a curiosity that was mistaken for lack of intelligence. Do you find it strange how we often project human traits like bravery or foolishness onto animals that are simply following their own evolutionary logic? The environment of Mauritius dictated a specific biological rhythm for these birds, one that involved a recurring cycle of feast and famine. Scientific analysis of contemporary accounts and skeletal remains suggests the dodo was a master of seasonal adaptation, capable of building up massive fat reserves during the island's lush periods to survive the harsher dry seasons. This fluctuation in weight likely contributed to the varying descriptions provided by early explorers, some of whom saw slim, agile birds, while others encountered the heavy, waddling figures that dominate our modern illustrations. Their anatomy was perfectly tuned to the forest floor, where they used their powerful hooked beaks to crack open the tough shells of endemic fruits and seeds. The tragedy of their disappearance was not solely the result of sailors hunting them for food, as is often recounted in simplified history books. While hunting certainly played a role, the true catalyst for their extinction was the accidental and intentional introduction of invasive species that the dodo had no way of countering. Pigs, rats, and crab-eating macaques, brought by visiting ships, proved to be an ecological wrecking ball for a bird that laid a single egg in a vulnerable nest on the ground. These new predators decimated the next generation before they could even hatch, leading to a population collapse that occurred with startling speed. Modern science continues to reclaim the dodo's dignity through the study of rare remains, most notably the Oxford dodo specimen held at the Oxford University Museum of Natural History. This parched piece of history has allowed researchers to extract fragmented DNA, confirming the bird's ancestral link to the Nicobar pigeon and revealing a much more complex genetic history than once assumed. Advanced CT scans of the Oxford skull have even suggested that the dodo's brain-to-body size ratio was comparable to that of other pigeons, indicating they possessed a level of intelligence that was perfectly adequate for their social and environmental needs. We are only now beginning to see the dodo not as a failure of nature, but as a masterpiece of island biogeography that was simply never given the chance to adapt to a world that changed too fast. The ocean's history holds a similarly haunting memory in the form of the stellar sea cow, a creature that challenges our understanding of how large a mammal can grow while subsisting purely on aquatic plants. While the manatees and dugongs we know today are synonymous with tropical lagoons and sun-drenched shallows, this northern relative thrived in the near-freezing waters of the Bering Sea. They were gargantuan animals, often reaching 30 feet in length and weighing as much as 10 metric tons, a scale that dwarfs any Sirenian currently inhabiting our oceans. Their discovery was a matter of survival for the crew of the Vitus Bering expedition in 1741, who found themselves stranded on a desolate island between Russia and Alaska. George Wilhelm Steller, the expedition's naturalist, spent his months of exile observing these gentle giants, noting that they moved through the water with a slow, rhythmic grace. Have you ever wondered what it would feel like to stand beside a creature that large, knowing it possessed no means of defense? Because they evolved in an environment devoid of large marine predators, they lacked the instinct to flee from humans. Their anatomy was specifically specialized for their environment, featuring a thick, bark-like skin that protected them from the abrasive ice and jagged rocks of the shoreline. This integument was so rugged that Steller compared it more to the bark of an ancient oak tree than the skin of a living animal. Perhaps most fascinating was their dental structure, or lack thereof. Instead of traditional teeth, they utilized two massive, white, horny plates, one on the palate and one on the mandible, to masticate the immense quantities of kelp they consumed daily. These keratinous plates were so effective at grinding fibrous seaweed that the animals could graze for hours at a time, their heads perpetually submerged while their massive bodies drifted at the surface. This extreme buoyancy was actually a physiological limitation, as their high fat content and massive lung capacity prevented them from diving deep into the water. Steller observed that they were intensely social, displaying a level of emotional complexity that few at the time could fathom. When a member of the group was harpooned, the others would often throw themselves across its body or attempt to nudge it away from the threat, refusing to leave their companion even as the danger escalated. This loyalty, while noble, proved to be their undoing. The ease with which they could be found and their reluctance to abandon wounded mates meant that hunting them required very little effort for the fur traders who followed Bering's path. By 1768, a mere 27 years after George Steller first sketched their likeness in his journals, the last of the species had vanished. This rapid extinction remains one of the fastest recorded disappearances of a large mammal in modern history. It serves as a stark reminder of the delicate balance within isolated ecosystems, where a single new variable can unravel millions of years of evolutionary adaptation in the blink of an eye. Even today, the skeletons of these majestic creatures, found partially buried in the sands of Bering Island, offer a silent testimony to a giant that lived without aggression in one of the harshest climates on Earth. While the sea cow vanished from the North Pacific, a similarly tragic story was unfolding across the vast expanses of the North Atlantic with the great auk. This bird, known scientifically as Pinguinus impennis, represents one of nature's most striking examples of convergent evolution. Though it bore a striking resemblance to the penguins of the southern hemisphere, with its flightless gait and stark black and white plumage, the great auk was entirely unrelated to them. It was actually a member of the Alcid family, making it a giant, flightless relative of the modern puffin and razorbill. Evolution had traded its ability to fly through the air for the capacity to fly through the water, transforming its wings into stiff, powerful paddles that could propel it to incredible depths in search of fish. This biological specialization allowed the great auk to thrive across a massive historical range, from the rocky shores of New England and Atlantic Canada to the misty cliffs of Iceland, Norway, and the British Isles. For centuries, these birds were so numerous that they served as essential landmarks for mariners, who knew they were approaching land when the distinctive white and black forms began to hit the waves. However, the very traits that made them masters of the sea made them defenseless on land. During the breeding season, they gathered in massive, dense colonies on low-lying islands, where they were easily approached by humans. Do you ever find yourself wondering what the world sounded like before the cacophony of modern machinery began to drown out the voices of the wilderness? For the great auk, the end came not through a single catastrophe, but through centuries of relentless exploitation. They were harvested in staggering numbers for their meat and their fat, which was rendered into oil for lamps. Most devastating was the trade in their down feathers, which were highly prized for stuffing mattresses and pillows. By the late 18th century, the bird was already becoming a rarity, a scarcity that unfortunately made it even more valuable to collectors and museums. The final chapter of their existence is one of the most precisely documented extinctions in biological history. By 1844, only a single breeding pair remained on the jagged, volcanic island of Elde off the coast of Iceland. On a June morning that year, 3 men climbed the cliffs to claim the birds for a merchant. In the ensuing struggle, the last 2 great auks were killed, and their only egg, the final hope for the species, was crushed under a boot. It is a haunting thought that we can pinpoint the exact moment a lineage millions of years in the making was extinguished. The cultural loss was profound, as a bird that once defined the maritime identity of the North Atlantic became nothing more than a ghost in the annals of natural history. The transition from the cold Atlantic to the rugged, temperate rainforests of Tasmania reveals another tragic silhouette in the history of lost species. Evolution frequently arrives at similar biological solutions through entirely different paths, a phenomenon known as convergent evolution. The thylacine is perhaps the most famous example of this, possessing a body plan that mimicked the wolves of the northern hemisphere despite being a marsupial. While it shared a common ancestor with dogs nearly 160 million years ago, its predatory lifestyle shaped its frame into a familiar, canine-like form. This creature was a master of the southern hemisphere's ecosystems, filling the niche of an apex hunter with a quiet, persistent efficiency. The physical reality of the thylacine was a blend of the familiar and the surreal. Its most iconic feature was the series of dark, transverse stripes that began at the midback and continued down to the base of its tail. Unlike the fluid, expressive tails of modern dogs, the thylacine's tail was thick and rigid, merging into the rump in a way that mirrored the skeletal structure of a kangaroo. This stiffness influenced the way it moved, resulting in a somewhat awkward, pacing gait. Historical records even describe the animal occasionally rising onto its hind legs or performing a series of bipedal hops when it needed to clear obstacles or flee from a perceived threat. The mechanics of its head were equally distinct, specifically regarding the incredible range of its gape. A thylacine could unhinge its jaws to an 80-degree angle, a feat that would look otherworldly to anyone accustomed to the anatomy of a domestic pet. While this wide mouth was intimidating, forensic analysis of its skull suggests that its bite force was actually quite weak. It likely focused on smaller marsupials rather than the large sheep it was later blamed for killing. Interestingly, the thylacine was one of only 2 marsupial species where both the male and the female possessed a pouch. In males, the pouch served as a protective sheath for external organs while they moved through the thick, abrasive undergrowth of the Tasmanian wilderness. The disappearance of this striped predator was a tragedy of human error and systemic mismanagement. During the late 19th and early 20th centuries, a culture of fear led the Tasmanian government and private livestock companies to establish aggressive bounty systems. They were labeled as vermin, and thousands were hunted for a meager financial reward. By the time scientists realized the population was in a terminal collapse, it was nearly too late. In a bitter twist of irony, the species was granted full legal protection only 2 months before the final known individual perished in a Hobart zoo. Do you find yourself wondering if there are still hidden pockets of wilderness where human eyes haven't looked for decades? This brings us to the enduring mystery that surrounds the animal today, a phenomenon that bridges the gap between biology and folklore. Hundreds of unverified sightings are reported every decade, often accompanied by blurry photographs or inconclusive paw prints. This persistent belief in their survival is what researchers call the psychology of hope. It represents our collective refusal to accept the finality of extinction and our longing to believe that the world is still large enough for a ghost to hide. While modern DNA sequencing offers a slim chance of de-extinction in the future, the thylacine currently remains a powerful symbol of what is lost when we fail to understand the balance of an ecosystem. The skies of North America once bore witness to a biological phenomenon so vast it remains difficult to comprehend through the lens of our modern, quieter world. While the thylacine lived in the shadows of the eucalyptus, the passenger pigeon existed in a state of constant, deafening visibility. Estimates from the mid-19th century suggest a population fluctuating between 3 and 5 billion individuals, making them perhaps the most numerous bird species on the planet at that time. When a flock took flight, the sheer density of bodies created a living eclipse that could last for several hours or even days, cooling the air temperature beneath the canopy as the sun was blotted out. Famous naturalists like John James Audubon described the sound of their wings as a roar like a gale-force wind, a collective energy that seemed inexhaustible. These birds were biological gamblers, relying entirely on a strategy known as predator satiation. By moving in massive, nomadic colonies, they ensured that even the most determined predators could only consume a fraction of the population, leaving the rest to thrive. This social structure was not just a preference but a biological necessity. The passenger pigeon was an obligate colonial nester, meaning they generally required the stimulation of a high-density crowd to even begin the process of mating. Without the presence of hundreds of thousands of their kin, their reproductive cycles simply would not engage. They followed the shifting abundance of the hardwood forests, seeking out the cyclical massed years of oaks and beeches where acorns and nuts were plentiful enough to fuel their immense caloric needs. The downfall of this feathered empire was accelerated by the very innovations that defined the Industrial Revolution. Before the advent of the telegraph, a flock could move through the wilderness undetected, but once wires stretched across the continent, news of a nesting site could be transmitted instantly to professional hunters hundreds of miles away. The expansion of the railroad system turned these birds from a local resource into a commercial commodity, allowing carloads of salted pigeon meat to be shipped to expanding urban markets in the East. It was a relentless convergence of cheap ammunition, efficient transport, and a total lack of conservation laws that decimated the population in a span of just a few decades. By the late 1800s, the once uncountable billions had fractured into small, isolated groups that lacked the social density required to successfully rear their young. Losing the passenger pigeon fundamentally altered the architecture of American forests. As the primary consumers of acorns, their absence left a massive surplus of food on the forest floor, which likely fueled the population explosions of white-footed mice and deer. The physical weight of the flocks also acted as a natural pruning mechanism, the mass of thousands of birds landing on a single tree would often snap large branches, creating light gaps in the canopy that allowed sun-loving pioneer species to grow. On September 1, 1914, the last known survivor, a female named Martha, died in her enclosure at the Cincinnati Zoo. She was the final heartbeat of a lineage that had once dictated the rhythm of a continent. Have you ever wondered how the forests near your own home might have looked if these great nomadic flocks still roamed the sky today? The silence that followed Martha's passing was not an isolated event, but a somber introduction to a modern era where biological histories are being erased with startling speed. One of the most significant losses occurred in the murky waters of the Yangtze River in China, the former home of the Baiji, or Yangtze River dolphin. This elegant, pale cetacean was the first of its kind to be driven to extinction by human activity, succumbing to the pressures of industrialization, dam construction, and the constant acoustic interference of heavy shipping traffic. For 20 million years, these dolphins used sophisticated sonar to navigate the river's depths, yet they were declared functionally extinct in 2006 after a comprehensive search failed to find a single individual. This loss signaled a turning point, proving that even large, charismatic mammals were not safe from the rapid transformation of their habitats. High in the misty mountains of Costa Rica, a different kind of disappearance was unfolding during the late 1980s. The golden toad, once famous for its brilliant, almost glowing orange skin, vanished from the Monteverde cloud forests in a remarkably short window of time. Its decline serves as a primary case study for scientists researching the intersection of climate change and disease. Shifting weather patterns altered the humidity of the forest floor, creating the perfect conditions for the chytrid fungus to thrive. This pathogen, which affects the way amphibians breathe through their skin, has since been identified as a leading cause of the global amphibian crisis, yet the golden toad remains its most famous early victim. In the Galapagos Islands, the passing of Lonesome George in 2012 marked the end of the Pinta Island tortoise lineage. George spent decades as a global icon of conservation, living at the Charles Darwin Research Station while researchers unsuccessfully sought a mate for him. His life and eventual death popularized the term endling, a word used to describe the very last known individual of a species. Being an endling represents a unique and profound biological solitude, where a creature survives as the final guardian of its genetic legacy. When an endling dies, the loss is not just an individual life, but the disappearance of specialized behaviors and ecological functions. These animals often served as ecosystem engineers, such as tortoises whose grazing habits shaped the vegetation of entire islands. Without them, the landscape loses its balance, and the intricate web of life begins to fray in ways we are only just beginning to understand. Scientists are currently attempting to bridge the gap between geological history and the present day through the ambitious field of de-extinction. While many people imagine cloning as the primary path, essentially creating a genetic twin from a preserved cell, this method is rarely viable for species that have been gone for centuries. Living cells are fragile and do not survive the passage of deep time. Instead, researchers turn to CRISPR, a sophisticated molecular tool that functions like a pair of genetic scissors. This technology allows scientists to take the genome of a living relative, such as the Asian elephant, and precisely edit its DNA to include traits found in the extinct woolly mammoth. The goal is not to create a carbon copy of the original animal, but rather a functional hybrid. This functional de-extinction focuses on specific phenotypes, such as thick subcutaneous fat layers, smaller ears to prevent heat loss, and the iconic shaggy hair. By introducing these traits into elephant embryos, scientists hope to create a creature capable of thriving in the sub-zero temperatures of the Arctic tundra. This process faces a significant hurdle in the form of DNA degradation. Even in the best-preserved specimens found in the Siberian permafrost, the genetic code breaks down into millions of tiny, scrambled fragments over time. Research published in the journal Nature suggests the half-life of DNA is approximately 521 years, meaning that after several thousand years, the biological blueprint becomes an incomplete puzzle with too many missing pieces. This chemical reality is why we can likely never recover dinosaurs, as their genetic information has long since vanished into the fossil record, leaving a void that even the most advanced technology cannot fill. Even if the genetic sequence is perfected, a biological body is only one half of a species. Behavior is often learned through social structures and parental guidance. An elephant-mammoth hybrid would be born into a world without elders to teach it the migration routes of the Pleistocene or the specific foraging techniques required for northern survival. How do you feel when you think about an animal being the first of its kind in 10,000 years, with no one to show it the way? The motivation behind this work is often rooted in the concept of Pleistocene rewilding. Proponents argue that bringing these ecosystem engineers back could help combat modern climate change. In the Siberian Arctic, large herbivores once trampled the deep snow, exposing the ground to the freezing air and keeping the permafrost stable. Without them, the snow acts as an insulating blanket, causing the ground to warm and release trapped methane. Reintroducing a mammoth-like hybrid could, in theory, restore this ancient cooling mechanism. Yet, serious ethical questions remain regarding resource allocation and the preservation of modern habitats. Critics point out that the staggering costs of de-extinction might be better spent protecting the endangered species currently on the brink of vanishing. The world has changed significantly since these animals last roamed the Earth, and finding a suitable habitat that isn't fragmented by human infrastructure remains a daunting challenge for any resurrected species. We must consider if it is responsible to bring a creature back into a world that may no longer have the space or the climate to support its ancient way of life. Survival has never been a guarantee. Yet the history of our planet is defined by a stubborn, persistent resilience that transcends the individual. Over the course of nearly 4 billion years, life has endured 5 catastrophic mass extinctions, each one stripping the biosphere of its dominant actors only to pave the way for a new, unexpected cast. From the Great Oxygenation Event to the asteroid that silenced the non-avian dinosaurs, these pulses of loss are not just endings, but the very mechanism of change that allows for the diversification of every lineage we see today. Every living creature carries within its genetic code a map of these ancient struggles, a biological ledger of those who navigated frozen oceans and volcanic winters. We are the inheritors of a legacy built on the foundations of those who are gone, linked by an unbroken thread of DNA to the trilobites of the Cambrian and the mammoths of the Pleistocene. The absence of these creatures serves as a quiet, profound reminder of the delicate equilibrium required to sustain complex ecosystems. When a species vanishes, it is rarely a solitary event. Instead, it is a ripple that moves through the web of life, altering the flow of nutrients, the growth of forests, and the behavior of predators. Observing the fossils of a vanished world allows us to appreciate the intricate craftsmanship of evolution, from the iridescent scales of ancient fish to the hollow, light-filled bones of the pterosaurs. There is a singular, quiet beauty in the realization that the Earth was once a home for giants and wonders we can only reconstruct through stone and imagination. These organisms were not failures of nature. They were magnificent adaptations to a world that shifted beneath their feet. As we look toward the future of conservation and the potential for scientific restoration, we are reminded that our role is to be thoughtful stewards of the biodiversity that remains. The study of extinction is ultimately a study of value, teaching us to cherish the vibrant, breathing world that surrounds us right now. Perhaps you find comfort in the vastness of this history as you drift toward sleep, knowing that you are part of a grand, continuing story of life on Earth. If you have enjoyed this exploration of the deep past, please consider subscribing to join us for more journeys through the wonders of the natural world. Sleep well, and may your curiosity remain as enduring as the life that has shaped our remarkable planet.